Hello, everyone. Let's start. Some of you have expressed interest about attending reading groups about diffusion models or other, tools in AI. So we'll add on Piazza information about a very interesting reading group that is going on right now on Robotics Institute. It's called MISS Reading Group. The topic is mostly about vision and robotics, but also it touches also sometimes on reinforcement learning. It's mostly a representational learning reading group, which is basically the cornerstone of anything else you want to do in AI. So I would highly recommend attending it. And today, for example, it happens every Wednesday, 3 to 4 in NSH. So you can go and, try today, see how you like it. It's going to be full of people. Most of them are masters and PhD students. And I think you'll find this useful. I think we have one reinforcement learning reading group, and I'll try to share information about this as well on Piazza, okay? Okay, Josh, I just sent you an email about this, basically. So let's start with our lecture today, which is evolutionary methods for policy search. So reinforcement learning, so our goal is again the same. We want to learn the parameters of our policy. The policy takes as input states, sensory input out of which squeezes state representation and maps to actions. And the goal is to maximize returns of trajectories and expectation. And we already know what's a trajectory, a sequence of state action rewards. And the return is the sum of rewards from now till the horizon, or a sum of discounted rewards from now till infinity. And so far, we discussed about dynamic programming, of course, in our first lectures, where we assumed the model of the environment and the reward function were known. Then we discussed about the value-based methods that try to estimate value functions, okay, from experience of the agent. We saw the tabular toy version as well as with functional approximation, which we said we can scale to real sensory input and continuous sets of states and so on. We talked about actor-critic methods. And today we will, focus on policy optimization. So we'll completely, give up on value functions. So we're not going to be trying to estimate values for states. In fact, we are going to completely forget that different states exist and that the agent transitions from one state to the next and so on. And there are recursions that you can use and so on. The reward can have a very general form. And we'll just approach policy search as a generic optimization problem. And let's see where this is going to take us. So we will use evolutionary methods. Probably you've already heard about this. These are just black box optimization methods that you can use for any problem. You don't need to incorporate domain knowledge. And we'll show why this is good or bad and how well it can scale and so on. Okay. So what is a black box optimization? Then our hope in the first set of slides is to understand the difference between this type of black box optimization and whatever we've been doing so far. Okay, so black box optimization for policy optimization, for policy search, essentially what it's going to do is you're going to be sample batch of policies, deploying them in the environment, compute the goodness of every policy based on the average returns of the trajectories, and then keep the best policy and so on, and mutate those, etc. So we'll follow the general strategy of, we have some policy parameters theta, and we're going to perturb those policy parameters, which means we're going to sample nearby vectors, theta i's, okay, by changing different coordinates of the original theta vector. Then the result will be a bunch of policies. Then we will run each one of these policies to the environment, collect trajectories, and evaluate the returns to be able to compute the fitness of each policy. The fitness is just a scalar value that tells you how well each perturbed parameter vector is actually doing. And then we'll promote, okay, and essentially reinforce essentially the policy parameters that resulted in trajectories that gave the largest returns on expectation based on our samples. All right. And so those perturbations that did well, we keep them. The perturbations that did badly, we forget them and discard them. And so we keep the perturbed vectors that did well and perturb those and so on. Okay, so why we call this black box? So what is the information that we have discarded here? Well, we've discarded anything that dynamic programming or the recursions that we use to estimate value functions. You see, all value functions are based on some recursive relationships. All these are gone now, okay? So we don't consider the structure and the environment. And you know what? If a particular state, if you move along and there's a trajectory and some state has high reward, probably the states before are also good and so on, you don't consider at all the interconnectivity of states in that, in this formulation. The only thing you do when you are given a trajectory is that you can compute a return and then average across trajectories to get a fitness score for the policy. All right. Yeah. So no gradient information is used, of course, anywhere, but not even no gradient is used, but even no information regarding the structure of the reward, and that is decomposed over time steps and so on and so forth. And it is additive over states, etc. Okay, so this is what we're going to do. I think it's super worthwhile to do that because, you know, at the end of the day, our policy gradients were also not all the way differentiable, right? We're only differentiated the policy network. What was coming out of the policy network was not differentiable. Now, at the end of the day, we want to know how much do you gain doing things like policy gradients or autocritic methods versus some black box optimization. Okay, and by the way, there is a huge discussion in the field about this, meaning how important are those algorithms and why instead we just do trial and error learning by just mutating the policy parameters, deploying the policy, seeing how well they are, and so on. Like much, much simpler way of optimizing our policy. Okay, so let's see. So the general algorithm will be something like this. We'll initialize a population of parameter vectors. By the way, parameter vectors are just the weights and the bias of the neural network. All right, that's what your parameters are. So you'll call those the genotypes. Then you'll start doing some random perturbations to each of those parameter vectors. So this perturbation we'll call mutations. You will evaluate its perturbation, all right, to compute a fitness score. And then you will keep the perturbed vectors if the result actually improves. All right. So look now what terminology we use: genotypes, mutations, fitness, and selection. Okay, this is precisely the terminology used in evolution. And that's exactly why we call this evolutionary methods. This is much like what nature does. All right. We have particular genes that are mutated, and those that prevail, those that the best one survives and the others go away. And it's interesting how the Omicron variants survived, right? Why? Because it was not killing its, its victims, right? So the Omicron variant of coronavirus prevailed over the previous one. So it's exactly the same thing that we're going to do here. So it's simple and it's biologically plausible. And now we'll go into the details of this process. Now, before we go into the details, I want to ask you which one of those steps you think is going to be the most computationally expensive. Yes.
The evaluation stuff.
Yes. Why the evaluation?
Because you need to run each agent that you created in the environment and then average the rewards.
The returns of the trajectories. Exactly. That's precisely right. The only thing that we need to consider when we go to those black box optimizers is the computation. All right. And indeed, the computation, estimating the fitness scores of policies, what is the most expensive. But the good thing about this is that it's crazy parallelizable, right? So every parameter vector can be evaluated in parallel, okay? You have different CPU nodes evaluating every perturbation and so on. Okay, so, I mean, clearly, the more accurate you are, the more perturbations you evaluate, right? You search much wider range, as well as the more trajectories you collect, because the more trajectories you collect make every fitness score more reliable. Clearly, right? By the law of large numbers, if you want to approximate the expectation, you really need to have lots of samples. And the more perturbations you have, the wider is your search in different parts of the parameter space. Okay? All right. So here is the Gaussian density in one dimension. And here is the multivariate Gaussian density. And I'm showing it because we'll assume that we're going to be sampling those parameters vectors for some Gaussian. So just nothing crazy here. We're just going to have some mean. We're going to fix the variance, and we're going to be sampling from that Gaussian. That's the perturbation essentially is going to be the Gaussian samples. That's fine. And based on the evaluation of those Gaussian samples, we're going to be moving these Gaussians, this Gaussian around, the mean of that Gaussian around, okay? So our goal is to find that mean so that samples under that Gaussian all give good fitness scores, okay? All right. So before we go to this way of sampling, I want to present two extremely simple evolutionary search methods. The first is going to be called cross-entropy method, and the other is going to be called CMA, covariance matrix adaptation. These work as follows. So the policy parameters are sampled from a multivariate Gaussian distribution. The covariance matrix is diagonal, and we'll update the mean and variances of those parameter elements towards the samples that has the highest fitness scores. Yeah, so it looks something like this. So you generate, you just sample, so you generate a set of parameter vectors by sampling from this initial Gaussian. You need to initialize mu and sigma somehow, all right? Then for each of the samples, you need to run trajectories and compute, this is specifically for some specific game that was developed, but basically evaluate trajectories. And then you define a hyperparameter, which is n, which tells you what is, rho, the proportion rho, that tells you what percentage of those perturbation vectors you want to select and to threshold. For example, let's say I want to keep the top 30%. So in this case, rho will be 0.3. So you keep that many of those parameter vectors. And based on this strict thresholding, right, hard threshold, you just recompute means and variances. That's pretty much it. And J index is essentially the coordinate of the mean and the variance. Okay, and we don't have a full covariance matrix here. We just assume that every parameter, every individual parameter is correlated from the other. So we just have one variance, and the non-diagonal elements are zero in our covariance matrix here. All right. That's it. We add also some eta here. Make sure that our variance do not collapse, because if they collapse, then how we're going to sample, right? It's the same problem with exploration, that we were boosting up our entropy of our policy, so that make sure that we keep exploring. All right, so exploration happens in the parameter space simply by sampling from this Gaussian distribution over the parameters of our network. Yes?
Crossover pattern happens by summation. You select the best people from population basically.
Yes, so you can call those elites. These are the elite parameter vectors. Yes, so you select the elites. Yes.
And then we do crossover and mutation, right? So I believe the noise is something like mutation.
What do you mean crossover?
So with genetic algorithm, once you have two best performing samples, then you try to select parts of each and combine them.
Yeah, so the combination here is you have your set of elites, you just compute the mean and the variances of those, and that's how you generate the Gaussian for the next round of this evolutionary search. Okay, so you don't mix and match parts at all. No, you just average those long vectors. Is that clear? Okay, this is super simple. You will see this in tons of papers. So now you know what it is. It's the cross-entropy method, CEM. So there is nothing. We just start very simple here. So by the way, this was the dominant approach for playing Atari till 2013. All right. And this works really well in low dimensions, for low dimensional policies. Now, how can you have a low dimensional policy? You need to engineer your features. And indeed, back then, many people were using these 22 Berteckas features because Berteckas had introduced those features for playing Tetris. All right. And yes, you can search on that very low dimensional, of course, parameter space easily with cross-entropy method. Okay. And now the natural question to everybody's brain should be, does the scale to hundreds of thousands of parameters that we need if we want our policy to be a neural network as opposed to a linear layer over engineered features. Is this clear? Okay, great. Now, beyond that question, I want to tell you that later in the course, we may ask you when you may have a model that you use to look ahead, etc. And then we ask you, oh, search over action sequences that you need to play to maximize your final reward under a frozen model. And the way you're going to search will be against some evolutionary search. We'll probably do some cross-entropy method. You will start with your actions, and then you'll evaluate them, and the action sequence that get higher reward, then you search around them, and so on. So my point is as follows. This search method can happen in any space. Here, it happens in the parameter space, which is has as many dimensions as the parameters of your policy. If you search in the action space, then that space is probably going to be much shorter, right? Whatever, different degrees of freedom you have on your actions, let's say steering angle or speed and so on. All right, just to be clear, the same CM can be used to search for policies or search for actions or search for anything you like. Okay, all right. Now, covariance matrix adaptation. Nothing different here. The only difference is that instead of having a diagonal covariance matrix, we have a full covariance matrix. That's it. And this is going to show up in the homework also to see how simple it is. So again, the idea is the same. I have some Gaussian, multivariate Gaussian on my parameter space. I sample from it. Okay. I evaluate each sample. So these numbers are the scores, the fitness scores. I take the elites. I say I want the top 50%. So whatever survives, we call them the elite of the population. And we fit a mean, and we also fit the covariance matrix. That's it. And we repeat, okay? That's all that happens. Is this clear? Okay, so we just saw two very, very widespread, evolutionary search methods. In fact, there is a very interesting NeurIPS paper with the title, Dynamic Programming Finally Performs Well in the Game of Tetris, that came around that time, that it was the first time where dynamic programming was able to beat these cross-entropy methods on finding policies for, let's say, Tetris. Okay, but basically these are very, widespread, optimization methods due to their simplicity, and because we know that we can just scale the resources and our algorithm naturally will perform better. Okay, we'll be able to search wider space, have more accurate fitness scores, and so on. So now we'll see the extreme of this algorithm. There is a great paper, 2017. I mean, it's kind of old now, but it's still extremely innovative because they were able to really scale this to neural networks. So there is a very interesting trick that we will discuss about how they managed to do that. Yes?
Is it more important in scaling this up to have more parallel simulators or more simulations per simulator?
Yes. So your question is it more important to have more parameter vectors or more trajectory samples to have good fitness scores? Both are insanely important, right? Because in accurate fitness scores, then you are going to select not the correct elites, right? Yeah. Okay. So let's see. So here is the algorithm. The algorithm is very simple. It's the implementation that matters. So just bear with me. So the algorithm is exactly what we saw earlier. And the only difference is that instead of having a hard threshold, we just have a weighted sum. So every offspring, every mutation has the fitness score, okay? And you weight the mean based on those fitness scores. That's it. And everybody participates. So both those that have high weight and those that have low weight. And we think that this is more elegant, let's say, okay? So that's all that happens. So how are we going to land now? Let's see how the math works out. Well, our goal is that to find the mean mu of the multivariate Gaussian distribution from where we're going to be sampling parameter vectors of the expectation of theta's parameter vector sampled under that Gaussian distribution of the fitness scores of those samples, right? Very simple way to put down our objective. Okay, now somehow this is very similar to the reinforcement learning objective. Do you remember the difference between this objective and what we had in policy gradients lecture? Again, we had an optimization over an expectation of things sampled under some distribution with some fitness of these things that were sampled. Do you remember? Here we're sampling parameter vectors. There, what did we sample? Trajectories. So we had some trajectories here sampled from some distribution, and the distribution was our policy essentially, right? Because what matters when you sample trajectories is the actions. And then here was the reward of those trajectories. And we show how that thing can also be written as expectation over actions directly, right? Which much clearer also, because then you say, oh, what's the probability of a trajectory? Well, the probability of an action is very clear, is your whatever your policy network assigns. And the goodness of every action was the rewards that come from that action onwards on your trajectories, if you remember. So we'll see those side by side in a couple of slides as well. So, okay, so we need to take a gradient with respect to mu. Now, interestingly, that mu is a variable that parameterizes the distribution inside the expectation. And because this happens, you cannot just push this gradient inside the expectation. Do you see? Because it depends on distribution. So if you remember what we did last time when this happened was, we said, okay, let's just write out that expectation. And we say, okay, now I can push it inside. And I need to make sure that, so now the problem where we got stuck is not on this gradient. Everybody knows how to compute that. This P is usually just a Gaussian. You just take a derivative of the Gaussian version to mu, right? It's just the square. So we know that the problem was that we had this intractable sum that we didn't know how to approximate because we only know how to approximate expectations. And then we said, okay, I can make it look like an expectation if I multiply and divide with mu of theta. And now what's inside the expectation changes a little bit, is whatever I had before divided by the P, the probability. And here is how things look like if I also use the chain rule for the logarithm. All right. So somehow we ended up with something extremely similar to the policy gradient lecture. And now the sum doesn't scare us anymore because we will just, it's an expectation and we'll approximate it with samples. And these samples is exactly those parameter vectors that we just discussed. We'll have our Gaussian, we'll be sampling from that Gaussian, we'll evaluate those guys, these are the F thetas there, and we'll be moving, the mu vector towards the samples that have the highest fitness scores, let's say. Okay. All right. Now, the fitness score itself is an expectation over trajectory sample from that policy parameters, the corresponding theta, and so on, right? But this is all under the hood. This is up to you to, make sure you parallelize and have enough resources to have accurate estimations of those expectations. Is that clear? Okay. So this is what we had seen in our policy gradient lecture is, and correctly, as you said, we had expectation over trajectories, probabilities over trajectories where the theta was parameterizing our policy and the returns of the trajectories. And here, this is what we have in this lecture, which, okay, let's see them next side by side, where our parameter is just this mu, right? The mean of that Gaussian, of this multivariate Gaussian. These are parameters we're trying to estimate, okay? Yeah, not the thetas. Is that clear? The mu is what we're searching for. So in both cases, we're sampling. In both cases, we're sampling. In one case, we're sampling actions. And in the other case, we're sampling what? Parameter vectors. And the other expectation over trajectories is all hidden inside that f of theta, the fitness score for a specific parameter vector. Okay? All right. Okay, great. So policy gradient sample in action space and evolutionary search samples in parameter space. Now, let's go a little bit into the details of this sampling. So it's exactly what we discussed in the last lecture. Let's go into the details of how we sample from Gaussian distributions and why, because that trick of that paper relies on that Gaussian sampling, okay, on the details. It is not the reparameterization trick. You're not going to see any gradients anywhere, but still, it's important to go into the details. And the details are extremely simple. So if I have the mu, which is what I'm trying to optimize over, and I have sigma, and to be honest, sigma will be fixed if that's okay with you guys. It's going to be some fixed diagonal matrix. All right. So if I want to sample, the way we sample from Gaussian distributions is this. This is what we said last time. Mu plus sigma epsilon. And the epsilons are random vectors from that fixed multivariate distribution that has zero mean vector and identity covariance matrix. Is that clear? And here that sigma is just a scalar and is shared across all dimensions. Okay. Okay. So notice that indeed, if you sample in this way, the mean of those samples is indeed mu, and the variance is indeed sigma square. So is everybody happy? Does everybody remember that this is how we sample from general? Okay. All right. So here I just repeated it. Maybe we can say it a little bit better than yesterday. So how do we sample from a Gaussian distribution if we have access to a uniform distribution? Well, the first thing is we form the CDF, cumulative distribution function. What is the cumulative distribution function? It's a function that in the x-axis you have the domain of your distribution, okay, the different elements, and on the y-axis you have the probability that if you sample a value from your distribution will lie to the left of that value on the x-axis, okay? So for example, for every value here on the x-axis, the y will be what? The area under the curve that lies to the left of that value, because this is precisely the probability with which any sample will lie to the left of the input x. Is that clear? This is just from the definition of CDF. And we said that now we'll invert the CDF. Instead of going from our domain of the distribution to cumulative probabilities, we'll go from cumulative probabilities to items in the domain. All right? And by the way, this cumulative probability, just to be clear, as we go to the right of the domain, the area under the curve is 1. And as we go to the left of the domain, the area under the curve is 0. Okay, that's why it goes from 0 to 1 here. So now we'll sample from our uniform distribution a value, which is something between 0 and 1, because we'll look at the uniform distribution over this specific interval of 0 to 1. We'll go to the inverse CDF, and the input now will be a cumulative distribution, and the output will be the x, and that x is exactly your sample. So now you found one-to-one mapping between something between 0 and 1 that your uniform distributions will spit out for you, and a value on the domain of the Gaussian. Okay, so now that's what we said last time, just to refresh. And we said, okay, now that we know how to sample from a Gaussian distribution, I also know how to sample from a general Gaussian distribution simply by translating and scaling the samples of this fixed Gaussian distribution of 0 mean and unit variance. Okay. Okay, great. So far, we just revised what we said yesterday. Now, let's see now the details. Let's see why things are important. So first of all, we said that we need to, if you remember, our gradient towards searching mu was grad log p theta of mu. So what is the log of p theta of mu? Is exactly this from the multivariate Gaussian distribution. Whatever is in the exponent, do you agree? Okay, now let's take the derivative of this. This is just a square, so it's going to be something like theta minus mu sigma square. Do you kind of agree? The derivative will return to mu, and that's why the minus is also gone. Are you cool with this? Okay, great. So now you know exactly how to form this grad mu log p mu of theta, and let's try to write our approximation for that gradient. Let's, ideally you want to draw multiple parameters vectors, as we said. Your colleague pointed out that, yes, he asked actually how important it is. It's very important to draw multiple of those, but let's assume for the sake of the argument, we only sample 2 parameter vectors, theta 1 and theta 2. Our goal is to form essentially that derivative estimator, that gradient estimator. So here is the summation. Capital N will be only 2, okay, theta 1 and theta 2. And let's plug them into our formula, okay, N becomes 2. F theta 1, F theta 2. Let's assume that you took the policy instantiated from theta 1 run it in your environment, collect bunch of trajectories, average their returns, and you got that scalar value f theta 1 that tells you on average what are the returns of the trajectories that result from your policy. And here is the same thing for your theta 2. And grad mu log p mu of theta is precisely this. Do you agree with this rewrite? Yeah. So the fitness scores are scalars, right? They're just plain scalars. Okay, so here it says RT1 as if you only sampled one trajectory from theta 1. You can just sample as many as you like and average them. All right, now my question for you is, can we simplify a little bit that expression? Who would like to help us to simplify it by using the form of the Gaussian sampling? What is the form of the Gaussian sampling? The fact that theta 1 is essentially mu plus sigma epsilon 1, where epsilons are essentially samples from that constant Gaussian distribution of zero mean and identical variance. Yes?
Well, you can just plug in like that for both theta 1 and theta 2, just like different epsilons, and then like, we just have sum of epsilons and then sum of greater.
Say it one more time. Oh, the mu's are going to go away, you're saying?
Sure, yeah.
Okay.
Times like the sum of epsilons. Or I guess both of your terms.
Yes, exactly. Exactly what you're saying. So I have the constant vectors here that I sampled multiplied with the fitness, correct? Yeah, so that's it. Yes, please.
That should be a theta 2, right?
Oh, yes.
Okay.
Yeah, that's a typo. Yeah, that's a typo. Thanks for pointing this out. So we'll fix this. So now if we look at the algorithm, it's exactly what you guys said. Okay. This is called evolutionary strategies. We iterate, we start from some initial mu, and then each time we sample a bunch of random vectors here. We compute the returns of the parameter samples, mu t plus sigma epsilon I. So the sigma seems to be constant. All right. So here, noise standard deviation sigma. So we compute the fitness scores, and then we update the mu in this way. All right. And alpha is a learning rate. How much you want to update the mu at each iteration, the mu vector at each iteration. It's exactly what you guys said. N is the number of the perturbations, the number of samples. Okay, like what we had as number of trajectories, now is the number of parameter vectors. Okay, now let's see. Is this enough? By the way, we haven't done anything intelligent so far. The trick has not been introduced. Okay, this is the obvious, just evolutionary search for, let's say, policy parameters. And here, basically, in natural evolutionary strategies, all of the offsprings participate. Each one is contributing based on its fitness. So if you have low fitness, then you'll contribute little. All right. Yeah. So we don't have a hard thresholding. That's all. I mean, this is not a big difference, but just to be clear, to put everything next to one another, in both cases, we have some update of that mean vector. Here we have a weighted sum over all the offsprings. Here we have a hard thresholding over using only the elites. That's the only difference. Okay, that's the only difference. Yes.
The growth where we put in epsilon in place of theta 1 minus mu by sigma. Theta 1 and mu are vectors here, right? Or
mu, yes, and they're as long as the parameters of my neural network policy. Yes.
So theta 1 minus mu just means like an element-wise vector?
Yes, of course. Yes. Yes, these are long vectors, guys, right? These are long vectors. Sigma here is a constant because it's the same sigma. I mean, it doesn't need to be. You can also have a different sigma for every fixed, for every, action coordinate, if you like. No, not action coordinate, parameter coordinate. These are also scalars. The fitness scores are also scalars. And epsilons are, again, super long vectors as long as your number of parameters. Okay. Okay, so let's try to implement that now on hardware and see if it makes sense. How would we implement it? I would assume we would have as many, let's say, nodes, CPU nodes or hardware nodes as those guys. the number of perturbations to make sure that we evaluate the fitness of each sample vector in parallel. I mean, this is supernatural to do. Now I want to ask you, imagine, does anybody want to suggest some other parallelization strategy? So this is the most natural thing that comes in mind. And I want to ask you, if we choose this thing to do, what the different workers need to communicate to one another?
They need to synchronize the vector and your fitness and the action.
So yes, which is what? So say it one more time. This guy here.
Yeah.
Okay, and how big is this?
It's a vector.
It is a vector. And how big is this?
What do you have?
Parameters.
Is the number of parameters of your network. So if you put 100,000 parameters in your network, you need to send those very, very long vectors to one another all the time, because this is a continuous optimization, right? You need to iterate all the time. So that's pretty heavy. These are very long vectors to be sending left and right. And as a result of this communication becomes the bottleneck, basically. So you cannot scale linearly with the number of workers. You may say, oh, I have 10,000 workers hanging around, but you cannot become 10,000 times faster because of this, of the bottleneck, okay, of this communication. Is that clear? Great. Now the question is, what can we do? And this is exactly what we're saying here. They work well on low-dimensional problems. How can we use the same on optimizing neural networks? Here is the paper that I'll discuss. And they say evolutionary starts as a scalable alternative to reinforcement learning. So that's a pretty bold title, and say, look, you don't need to do all the methods that you learn in your RL courses. You can just do a smart implementation of evolutionary search. Okay, that's what this is saying. And let's see. So let's see what is their trick. The main contribution of the paper is that they managed to parallelize by sending tiny little things across workers, okay? So here is our workers, and let's say we have 6 of them, and we'll be evaluating 6 parameter vectors in parallel. So every worker gets a set of nothing. Every worker gets a parameter vector and then deploys it, takes the corresponding policy and deploys and collects batch of trajectories. And the master needs to average those, vectors essentially, which is epsilon multiplied with the fitness. Okay, this is what we saw here. This is each one of f multiplied with epsilon is essentially a gradient direction towards which you need to move your mu. Okay, so who would like to take a guess on how can we save? How can we save here? Yeah, so big gradient vector, so we don't want that. Yeah.
Line number 4 can be split across. Line number 4 is not dependent on time or anything, right? Those are just samples drawn from normal 0.
These guys, it's the epsilons.
Yeah.
Yes, so the epsilons are sampled from constant distributions. Okay, these are sampled from constant distributions. Yes. So it doesn't depend, this constant distribution is constant, it doesn't change over time. Okay, so here's the trick. They said, we're going to have a bunch of workers, and every worker will know the random seed of every other worker. Okay, so if you're worker I, you'll have, let's say, 1,000 random seeds for all the other 1,000 workers. So the other workers will be sampling their epsilons, and you will know what these are, because the random seeds will be, you all know the randomness of the other. And you are not going to be sending the epsilons through the bus. The epsilons will be sampled locally within each node. Of course, we're going to do much more sampling, because now I should not just be sampling for myself, but also for the other 1,000 workers. That is super cheap. Do you see the communication is the problem? Is that clear? Okay, great. So now we will not need to share the epsilons. What do we only need to share with one another?
And like what?
Yes.
The F scores.
Yeah, just the fitness scores. And you don't need to send from which random you came. That's precisely what you don't want to say, because basically, actually, no. Well, of course, you need to pair. You need to say, I'm number 3. Sure. Right, exactly. So that's it. Just the fitness scores. Let's not call them rewards, because we may kind of confuse them with the rewards of trajectories. Yes. Yes.
Can we not increase the computations that every worker has to do?
Yes, of course.
Everyone has to sum up everyone else's epsilon and x and their own.
Yes, but this is okay. This is not that terrible. It's just a summation. Yeah. And we need to sample, of course, 1,000 times more, right? So everyone needs to sample for everybody. The same vector will be sampled 1,000 times if you have 1,000 workers now, right? Because the random vectors of worker 3 need to be known to all the other workers, okay? Okay, great. So that's essentially the trick. Here is the pseudocode. Let's see how it looks like. We have a learning rate, some constant sigma, sure, and some initial parameters theta 0. We have n workers. They know we have non-random seeds and all have the same initial parameters theta 0, and we iterate. And each worker samples epsilon I and computes its returns. Okay, sure. Which are mu minus sigma of the epsilon I. And then we send all the scalar values to each other. And for each worker, we do the following. We reconstruct all the perturbations epsilon j's. Okay, so this is the sampling that happens in every worker. And then we form the updated mu. So now we all have the same mu, but without really communicating to one another. Okay, which is great. Okay. And so now every worker only broadcasts those tiny scalars, those fitness scores that you guys said. And as you see, we have great scaling. The more a course, so here they use 1,440. You see the time to compute the solution drops linearly, right? This is perfect scaling, okay? Otherwise, you would see some saturation, like due to the communication bottleneck. So this is part of your required readings, guys. So any questions now? Any questions? So let me ask you, I'll ask a question. Can evolutionary search get stuck in local optima? Yes, of course it can get stuck in local optima. You increase your compute and you help it find some better solution, but of course it can get stuck in local optima, okay? Do you have other questions? Yes.
Does it also depend on the initialization, like the theta zero that you existed?
Yes, but unfortunately, you cannot do much about that, right? You will just initialize your weights close to 0 somewhere. You cannot do some intelligent initialization.
And like the assumption that you're making that the policy parameter are Gaussian distributed, is it like a valid assumption to be made for a general scenario for it to work in any particular case?
Yeah, so we don't do any assumption. We just use the Gaussian distribution just for the sake of perturbation, make the perturbation easy. So instead of just taking vectors and ourselves going and doing some other weird way of mutating them, we just said, okay, what if we have Gaussian and we just sample and these are the perturbations? I think that makes sense.
But would that like limit us exploring like different places? Like with Gaussian, we tend to like explore within like within an upside and one within. So if we had some other kind of assumption, would that allow us to like explore different policies more?
Okay, so sure, I see your point. So what you're saying is, why don't we do a grid search over this high dimensional parameter space, which seems impossible? Yeah. So by the way, gradient descent in neural networks are also pretty local, right? You start somewhere and then you. But I see your point. Right. So there is not that many other solutions you can do in such a high dimensions. Do you see what I mean? It's not like I have 6 dimensions, let me chop them up and then search in each one, etc.
I was just thinking that if we could have taken any other assumption other than Gaussian.
Like what, for example?
Yeah, not sure.
Because that Gaussian can be wide. You fix the sigma. The sigma can be pretty wide. You can also make it wider in the beginning and shrink it later to allow it to explore more wildly in the beginning, right? Yeah. But here is now. So now we'll discuss something else, which is, yes, how can we get evolutionary search to be less stuck in local optima? This is the question. All right, and now it becomes a bit philosophical. So there is this paper we'll discuss now that says the following thing: it helps if you don't search only for one task, right? So here our goal was to make the cheetah, for example, walk fast. You remember the cheetah from the previous lecture? And your only goal was, I want to find a policy that actually makes the cheetah walk fast. What if we jointly search across a family of related tasks? Okay. For example, maybe I want to make the cheetah walk fast with using one leg more than the other. Maybe I want to make the cheetah walk fast while spending some time above the ground. So I put some constraints, let's say, on my behavior that I want to generate and I want to optimize for. And all these behaviors will be kind of related, like they're all about walking or they're all about manipulation. Okay. And instead of searching for only one task, we'll be searching jointly across multiple tasks. So what does this mean? What does this mean to jointly search across multiple tasks with evolutionary search? It means the following thing. You have your set of tasks. It's a big map, let's say 10,000 tasks. These 10,000 tasks, just to be clear, they're generated automatically by saying, I want the cheetah to be using K% of front leg and 1 minus K of the back leg. All right, and you vary K, and you'll generate different behaviors, like the different desiderata of behaviors, all right? Something like this. Or, okay, so that's one thing. And you have a map of different things you care to optimize, and you do a search, evolutionary search across all of them jointly. What does this mean? It means that each time you initialize all the parameter vectors for each one of them, and then you'll take one, you perturb it, as we said, and instead of just evaluating for fitness for this specific task, you evaluate for fitness for all tasks you care about. So maybe a particular perturbation is really bad for, let's say, walking up straight, but maybe it's very good for walking faster, for example. Do you see? And so basically, so that's the important detail. The important detail is once you perturb, instead of computing one fitness score, you compute 10,000 fitness scores for all those tasks. Of course, this is very expensive, but and then if indeed it's better than what you had before for a particular task, then you use it and you substitute it. All right, and then you repeat. Okay, you grab one, you perturb it, see if you improved, because for each task you keep the best performer so far, and you move on like this. And I think it's very interesting how by searching across tasks, you do better than by searching only across one task. All right, so let's see this paper specifically. So yeah, so this comes from a team of Jeff Clune, and the paper that we'll present is the number 1. So searching for policies across multiple related tasks. Now he has another paper where he searches for policies across multiple related environments. It's called POET. You can check it. It's actually very simple. Basically, you want to learn to walk, but instead of deploying that policy in one environment, let's say straight terrain, you add, environments with holes, environments with a little bit of hills. And, and the interesting part from that POET paper that we're not going to take is the following. If you optimize with evolutionary search for working on the straight terrain, you essentially get stuck on some local optima that does like this, the robot. But if you search jointly across all terrains, then you actually discover the right behavior on the straight terrain as well. So by jointly searching across multiple environments, you actually get less stuck in a local minima for a particular environment you care about. Is that clear? Okay, now this is not what we're going to discuss in detail now. We're going to discuss number 1. How do we search in the same environment, but for different behaviors, all related to one another? Okay. All right. So by the way, we don't have any guarantees or about this. These are all empirical results, just to be clear. So the idea is the following. Instead of searching for policy for one single task or one specific goal, jointly search for policies for multiple tasks. Then parameter vectors for some tasks and goals can be good stepping stones for another task. So I remember when, Jeff Bloom was talking about this idea, he also talked how important, he said this, for example, many things in science were accidentally discovered. You were looking for A, and actually we found magnetism. You were looking for something else, and actually you found, let's say, I don't remember what example he showed. So it's also very important in your research not to be super narrow focused, right? Because if you search across wide range of goals, okay, maybe in one goal you'll find something that, one direction search for one goal will end up being not good for that specific goal, but good for some other goal. Do you see what I mean? So multitasking overall is good. I think that's the idea here. But let's look at the specifics about the robots. So first of all, we need to decide what is this task. Okay, what are the tasks we're going to care about? And specifically, these people grabbed that little robot that has 6 legs, and they decided. So the first thing you need to do when you want to do this multitask evolutionary search is to decide these behaviors. So these people made descriptions. They made 6-dimensional descriptions regarding how much you can use every leg. Okay, so that's how they automatically generated a huge number of different desiderata for policies. So the different behavioral dimensions could be the percentage that each robot leg is being activated. Okay. So for grasping, you need to do something else and so on. And so now you're going to do evolutionary search, and you for high-performing policies for multiple different specifications of behavior in a grid-like multidimensional map. And in each cell of that map that I'm going to show, we keep the highest performing policy for that behavioral cell. So I don't keep only one guy who is like the best, like the mean over Gaussian, right? We have multiple means, one for each behavior. For example, this is the parameters of the best policy that can walk by using 20% of the front left leg and, uniformly the rest of us. And here is this other cell is the best performing policy, like parameters of policy that I have found so far that actually uses half of the time the front legs and half of the time the back and so on. And I'll show you why it's important to be able to learn those multiple policies. Now at this time, I want to pick the best performing policy in a new environment and in a new robot configuration. And the good thing is because I have learned multiple policies, then I have multiple options. Maybe one policy is not going to do well, but maybe some other will do well. Now, of course, you have a search problem in that new environment for finding that policy. So you need to deploy multiple ones to see what actually works. And you will see, we'll say what happens. In the same way, when you break your leg, you don't learn then to start working with the broken leg, right? You already have learned how to hop when you were healthy, when you had both your legs, okay? That's the idea here. So here is the archive of the elites, and we'll call them elites because every cell has the best performing policy for that subtask. And what we're going to be doing is yes, the map is going to be with this discretization. And the idea is perturb, locate, replace if better, and repeat. So what happens is you grab one parameter vector. So let's say this guy, I grab the parameter vector of that cell, I perturb it, I deploy it, I evaluate it, compute its fitness score, and then I compare it to the fitness scores that I have in the map. And if the fitness score of my perturbation is higher than any cell, then I go ahead and swap it. Is that clear? You see, I grabbed the parameter vector from the blue cell and I perturbed it, and I was not able to outperform the policy that was in the blue cell, but I was able to outperform the policy in the yellow cell. Okay, yes.
So blue cell is evaluated at a different weight height than the yellow cell, right?
Yes, it's evaluated in different ways, which means what? Yes, you deploy it on the robot and you collect trajectories and you see how fast it can move.
But it feels wrong to say that it's outperformed the yellow because the yellow is a different environment or a different, I don't know, slightly different task.
Yes. So we never compare blue and yellow. No. So you take the blue, the parameter vector that sits on the blue, that has a specific constraint. For example, use the front lead 30% of the time. Okay. And then you perturb, and then you get a new fitness score. Okay. And this perturbation happens for every behavior. You see? So you run multiple fitness scores and you compute, did I manage under this constraint of that cell, get a fitness score that outperforms the previous one or no? And you know what? I was not able to outperform the previous blue, but I was able to outperform the previous yellow. So under the constraints of the yellow cell, I actually did better. I moved faster.
So the evaluation step is over the whole grid then?
Yes, you need to be computing fitness scores under all behavioral, let's say, descriptions. Yeah. Right. Okay. So for example, for sums, you need to completely disable one leg. For sums, you need to disable 2 legs and so on. So you never compare a robot using 6 legs with a robot using 4. You all compare using 4 and using 4 after the perturbation. But for all those descriptions, the policy will have the same number of parameters, of course. Okay. So here is a real robot. And so now you did this learning, and this learning, took some time because you need to compute best performing policies for a gazillion different behavioral descriptions. And this algorithm called map elites, and it's a massive search space. Yes, and it after the end of the search, you have 13,000 diverse high-performing gates, essentially. All right. And you learn this from the undamaged simulated robot. All right. This all runs in simulation. Okay. And okay, now you go in the real world on the real robot, and you want to figure out which out of those 10,000 policies I need to use. And then you say, let me try the high performing ones. And all the high performing ones around that, the red is how fast you went with each policy. I mean, clearly, if you only use 3 legs, you're going to be yellow. You cannot be red. The other cell that use 6 legs will go faster. All right. So the important thing here is when you sample at test time, to sample and take into account the diversity. All right. You cannot be sampling all the time the same policy. So how do we sample with diversity? We use Bayesian optimizations, which I'll discuss right now. So this type of sampling is not, because you sample 3 policies and all sit very near in the map, so they are not very diverse. So instead, we'll use, as we said, Bayesian optimization. Now I'll tell you how this works. So I'll sample one policy and I'll evaluate in the environment, meaning my real robot will, use it. You see how fast I went. You don't have much time to run a lot of trajectories. You'll take few trajectories, and then you'll go and update the value. Okay, and you're going to have a fitness essentially function that is parameterized from X and Y of that map. Okay, and you'll see that actually that policy that you sampled really didn't do well. So now the whole map became blue. Okay, and then you say, oh, let me sample again, and then you sample from the next location and so on. So in Bayesian optimization, things look like this. You are trying to compute essentially that curve. In the beginning, you don't have a clue, so it's you have high uncertainty and so on. But as samples comes, and every sample is a deployment of the policy on the robot, essentially that curve is updated and so on. And as you see, wherever you have the dots, the uncertainty goes to 0, and then the uncertainty on the other locations is very high. We can actually, this might be a good idea for a recitation. We can go through, if you want, Gaussian processes and Bayesian optimization. For the undergraduate version of the course, we have a lecture. For here, we can have a lecture or just put it in the recitation, whatever you guys prefer. And then you will know exactly what happens here. Okay, the important thing is to balance the uncertainty of a particular regime of the map with them actually exploiting the scores. So it's again a balance of exploration versus exploitation while you're choosing locations of the map to evaluate. So that's it. And here is the video that I would like you to listen to. Okay, let's see.
Robots that can adapt like natural animals. A paper in Nature that describes damage recovery in robots via the intelligent trial and error algorithm. How can we get robots like these to adapt to damage like natural animals? Before deployment, a robot uses a novel algorithm to autonomously create a map of different ways to behave and the value of each behavior. Here is a variety of entirely different ways to walk produced by this algorithm. Note that the behaviors are only tested in simulation at this point. The discovered behaviors create a map of the behavior performance space. The map shown was created with the MapOmeets algorithm and contains the robot's intuitions about different ways to move and predicted performance of each way of moving. Now see the undamaged robot controlled by a classic tripod gate. Note that the robot moves straight and at a speed of 0.25 meters per second. The robot has now become damaged. Let's see if it can still walk. Unfortunately, this robot, like most robots, no longer works if damaged. Because the pre-damaged behavior no longer works, the robot needs to adapt. The robot conducts a handful of experiments to determine the behavior that still works despite the damage. To do so, it combines Bayesian optimization with its intuitions about behavior performance space provided by the map from the MapOmeets algorithm. Here is the first gate from the map it tries. Each experiment updates the robot's understanding of which behaviors work and which do not. After the map is updated with this new information, a new type of behavior is tested by choosing a high-performing behavior from a different region of the map. The map is then updated based on that experiment, and the process repeats. Note that the map is getting more blue over time, meaning that the robot is learning that most of the performance predictions from simulation on the undamaged robot do not perform that well on the real damaged robot. In less than 40 seconds, the algorithm has discovered a gate that's nearly as effective as the original. Because the map predicts a better gate may still exist, the robot conducts one more test, but that prediction turns out to be wrong. The intelligent trial and error algorithm thus terminates, selecting the best gate found, which is nearly as fast and straight as the original. Watching the gate in slow motion reveals that it is dynamic and really seems natural. It almost looks like a wounded animal limping away.
Okay. Oh, sorry. So, all right. Now, having said that, there is a more recent method that I want that we will cover in this course about robot adaptation, which instead of having around a discrete set of policies, essentially you learn one policy, but you feed to that policy not just the current state, but also an embedding on the environment conditions. What is an embedding of the environment conditions? You train yourself in simulation, and in simulation you have access to the coefficient of friction, you have access to the weight of the robot, you have access to other parameters of the environment. So you list those parameters and you put some MLP and you get a deep latent embedding there, like embedding vector, and that embedding vector enters into your policy. And you train your single policy under a gazillion set of environments. So this is what we're going to see in the domain randomization lecture. All right. So instead of learning to walk or to do well in one environment, you actually do well on a gazillion set of environments. And by the way, this is extremely powerful idea. Like domain randomization, we have a whole lecture on this. Now here is the difference between that paper that also had very similar goal of robots adapting is you don't learn one policy to be robust across all environment changes, which means I have one policy, state to action, but I train it across tons of environments. No, you make the policy be aware of which environment you are in by feeding that vector. And then at test time, you use your history of actions, essentially actions, observations, and feedback from your sensors to predict that vector. To say, oh yeah, I'm in this condition. So now my policy should be like this. Oh, I'm in this condition because now history runs, right? So as the history changes, your environment guess changes. All right. So you can do very similar cool stuff, but by having one policy that takes as input not that state and action, but right state, environment, condition, and action. And I think the best place to see that is in our domain randomization lecture. Okay, so not today, basically. All right. So that's the end of today's lecture. It's a bit shorter than usual, but on Monday, we will talk about imitation learning. Okay. Best of luck for Friday.